All right, folks, let's get started. Welcome to the Apache Sedona Community Office Hour this month. And as usual, let's quickly go through what Sedona is and some introduction about Sedona. So first, Sedona is an open source cluster computing engine for processing large-scale geospatial data. And we have Sedona source code hosted under the Apache Software Foundation on GitHub. And we also have LinkedIn account as well as Twitter account. So if you want to know the latest news of Sedona, please follow us on social media and make sure you stay tuned. So status of Sedona. So Sedona is being used by many companies in production. So there are many logos on the right-hand side. And so Sedona is a research project we initially started in 2015. And it became mature in 2017, and it joined the Apache Software Foundation in 2020. So it has more than 10,000 corporate users. On GitHub, if you go to our GitHub page, you will see we have more than 120 contributors on GitHub, and we have 2,000 stars on GitHub. And last month, its monthly downloads has exceeded 2 million downloads, and the overall downloads of Sedona has exceeded 40 millions. So this actually places Sedona among the top 0.3% most downloaded package on PyPy. So many people using Sedona, and I recently did uh, a little bit iteration about the Sedona community growth. So here are two charts. The chart on the left, it shows the overall downloads of Sedona per month in the past few years. As you see, the download of Sedona grows exponentially. And thank you all for helping us and for the support to Sedona. And the chart on the right shows the cumulative commits of Sedona per year. And as you can see here, so this project started in 2015, and we are receiving lots of commits from the community. So there are many contributors participate in the project and contribute back. And as usual, so if you have any new ideas or anything you want to add to the project, even just fixing the document, it is extremely appreciated. And you are welcome to uh, create a PR, create a GitHub issue, and a Jira ticket. And we welcome any kind of contribution to the community. So a quick overview about Sedona's system architecture. As you see on the right, so Sedona has multiple layers. The first layer is the spatial query processing layer. So it provides the spatial SQL API that actually allows you to interact with the system through the SQL interface. But on the other hand, it also provides Python, Scala, Java API. So it integrates with multiple developer tools such as Jupyter Notebook, GeoPandas, as well as RStudio, so on and so forth. And in this query processing layer, it also equipped with a bunch of distributed query algorithm. For example, k-nearest neighbor join query, spatial join query, and spatial range query. It also works with vector data and raster data together in the same query engine. And after that, we have the distributed spatial datasets layer. It basically organizes the spatial data structure inside Apache Sedona. So it has spatial data partitioning. It basically partition data across machines in the cluster. And it also has spatial indexing that index data on each machine to speed up query processing. And at the bottom, it has the distributed engine layer. So Sedona right now runs on top of multiple different engines. Apache Spark for batch processing, Apache Flink for stream data processing, and on Snowflake. So we have a Snowflake extension on Snowflake, and that is you can install it yourself. We also have a pre-compiled version on Snowflake Marketplace. So if you're interested, you can go to Snowflake Marketplace And this app is this native app is called Sedona Snow. It is a free app, so if you're interested, just search for it and you can install it. But by far, among all the engine supports, so our support on Apache Spark is the most performant and the most comprehensive one. Oh, okay. So if you want to give it a try of Sedona, so the easiest way to try Sedona, as always, is through Sedona Docker image. So if you have Docker installed on your laptop, you can go to Docker Hub and Docker pull the Sedona image and try to run it on your local machine. And so the details of the Docker image tutorial is available on our website. So if you go to the website, you can actually find the tutorial there. But the Docker image one is probably the easiest one for you to get started. Of course, this does not come with a cluster setting. So in the sense that if you want to have a hosted version, or if you want to have a real cluster, you need to probably look for a hosted version of Apache Spark on some cloud vendors, such as variables such as EMR, Databricks. Cool. So Sedona releases. So Sedona usually follows the 3 months release cadence. And we made a couple releases this year. So one release is in May, in August, as well as we recently made a new release of Sedona 1.7. And some of you probably have heard of it. And it is a pretty big release. It has many new features. And today I'm going to go through some key features that were released in this 1.7 release. And we also, uh, fortunately, we also invited one of the contributor of that function, James, in the call. So later he will talk about the GeoStats new feature in this 1.7 release. Cool. So what's new in Sedona 1.7? So one important feature we added in this 1.7 release is the k-nearest neighbor join operator. And if you joined us before, so we have mentioned this a couple times. So this is a new spatial join data type, spatial join operator type we added in this new release. Another one is the GeoStats. So GeoStats is the scalable spatial statistics toolbox that actually allows you to perform statistic analysis on spatial data. So GeoStats is a statistic toolbox. You can perform many interesting analysis on spatial data, and James later will give a very detailed explanation about what it is. And another important features is the data frame-based readers. So the database, so we in the past we have had a couple of very interesting spatial data set readers, such as shapefile reader, GeoJSON reader. But all these readers, they are kind of like hacky, so they do not work with the Spark data frame based readers natively. So we recently in 1.7 release, we introduced native data frame based reader. So that means couple benefits. So the first benefit is you get the tables directly out of the box. Secondly, it preserves the data type, in particular in shapefile and GeoJSON files. So the data that was stored in these files, it comes with data type. So this data type, if you use the reader we had in the past, many of them they lose the data type. So this time the data type going to be preserved, and you'll be able to process all that. So for KNN Join, right? So for people who attend the call the first time, so let's talk about what it is, and also I'm going to give you some example to help you understand what it is. So uh, let's assume there are two tables. So we have a restaurant table and we have a driver table. In the restaurant table, we have the locations of a bunch of restaurants, and in the driver table, we have the locations of a number of drivers. So the question I'm going to ask is, so how can I find the closest restaurant per driver? So this is the so-called k-nearest neighbor join. So in order to do that in Apache Sedona, so you can actually use the latest k-nearest neighbor join operator introduced by us. So it is called STKNN. So look at this query. So this still it is kind of like a spatial join query. In the from clause, you put two tables there. So the restaurant table and driver table. And in the where clause in particular, you're going to use this st underscore KNN function. In this function, you put two columns in as the input, location of restaurant and location of driver. And there is the third argument there is one. One means you just want the top closed restaurant per driver. So that's why you put one. So but if you want to have like two, three neighbors, right? That's why it is called KNN, right? If you want to have different number of neighbors, you can put different number there. So give it this number, right? So Sedona will actually return one driver per restaurant. So that is the closest one restaurant per driver. That is the closest restaurant per driver. So in practice, K-nearest neighbor join has many interesting applications, right? So here is a formal definition of the K-nearest neighbor join. So a KNN join operator involves two data sets. So basically, for the record in the first data set, it finds the key nearest neighbor from a second data set based on given distance metric. So the current example I gave you just now, it is one way to trigger the join. Another way to trigger the join is use the join operator explicitly, as you see here. So use the join operator, and the join condition is the STKN. So as I said, uh, K-nearest neighbor join has lots of interesting applications in practice. So for example, the screenshot on the left-hand side is a screenshot I took from the Redfin. So basically, you can use the KNN join to find for example, the nearest public school per real estate property per house, right? You can use that to determine uh, the education score for the uh, for the for the real estate property. Cool. So I saw there are quite a couple interesting questions. So I, there's one question about is STKNN available in the Snowflake implementation? So unfortunately, that is not available in Snowflake implementation. So because this new operator requires some deep optimization with the query engine, so that is not available to us through Snowflake. So that's why we don't have it in Snowflake. So it is only available in our Apache Spark implementation because this is changing the entire query algorithm, the query plan in the query engine. Okay. Another interesting question. So does the KNN join work with other type of geometries rather than points on the query and object side of the join? So this is a great question actually. So in this first release, we only focus on point object for this KNN join, right? Because calculate the distance among non-point object is much more complicated. But we are looking to add the support soon, as we are also exploring the most efficient way to do that. But other type of spatial join like range join, distance join, they all work with non-point data. I also want to add to the KNN join. So although I said it only work with point. In fact, you can still give it polygon, give it like trajectories. Any non-point data it will work with the k-nearest neighbor join. So the way we did it is, so when we do the k-nearest neighbor join for any non-point data, we don't take a centroid, take centroid out of the point, and use that to perform the k-nearest neighbor join. So essentially, it's work with non-point data, but the distance calculation may not as accurate as the point object. Cool. All right. So this is the Yeah, one example about the k-nearest neighbor join, as I mentioned, is to use it for the real estate to calculate to find the nearest object, like public school around each real estate property. Another interesting use case is actually for reverse geocoding. So not sure if you guys heard of reverse geocoding. So basically, this is a classic geospatial geospatial problem. Essentially, you give a spatial location coordinate and tries to match that to address, right? So that way, if you just say this is a ride sharing app, you want to pick up passenger, right? But this passenger give you a GPS location, and the software will match it to a real address. So the driver can use that address to locate this passenger. So uh, the algorithm behind the reverse geocoding is pretty much similar to the k-nearest neighbor join. The difference is you have many objects needs to be mapped to addresses. In that case, the k-nearest neighbor join is a very good operator for that. Cool. Regarding algorithm, so the k-nearest neighbor join is a very complicated algorithm, and uh, if you guys know the algorithm we use for regular spatial join, the distance join and range join, right? So one key algorithm we need to use is we need to solve key problem we need to solve is the spatial data partitioning, right? We need to partition both data sets based on their spatial proximity, and after that, we should be able to join them together based on the spatial proximity, right? So like California partition is going to be joined with the California partition, uh, Washington partition joined with the Washington partition from both data sets. So that way we don't spend time on checking irrelevant partitions. So this problem is actually much harder when it comes to the nearest neighbor join, because if you look at the data partition problem here, right? So we have two data sets, the green point and the red point. So they are from two different data sets. And we can actually use our original spatial partition method to partition these two data sets. And so this dashed rectangles, right? So they are the partition boundaries, spatial partition boundaries of the two data set. However, you cannot directly use that to perform the k-nearest neighbor join. Think about that. If you are looking for the say if if you're looking for the neighbors of this red point, right? This red point. So its nearest neighbor is not guaranteed to be in the same spatial partition with it, right? So if you just use the original spatial partitioning we had in Apache Sedona, so it will actually miss some of the nearest neighbors, right? It will not give you the accurate result. So in order to solve that problem, uh, so there's a complicated math behind it, but in short, what we did is so we introduced a small buffer around each object. So in this case, the query dataset is a red point. We introduce a buffer around each red point in this red dataset, and this buffer will actually enlarge the spatial partition boundary. And it kind of introduce a buffer area, and to make sure that all its neighbor is covered in the same partition. Okay, there is another interesting question. So how far could be the nearest neighbor? So that's a good point. So the key is we don't know, right? So this key nearest neighbor query does not specify by nature how far the neighbor could be. So that's why it introduced all sorts of issues when it comes to the spatial partitioning, right? Because we don't know how far the neighbor could be. So the nearest neighbor could be very far away. Suppose if you have a point that is so remote and you want to find its nearest neighbor, so the nearest neighbor could be really far away. So we don't know. We don't know where it is. Okay. But in the next release, set on the 1.71 release, so we are looking to add a new operator, a new k-nearest neighbor join operator to Sedona. So that is called distance bounded k-nearest neighbor join. So essentially it tries to limit the problem, try to kind of optimize performance. So basically, this is to address that. So in some cases, the nearest neighbor could be really far away from the query point, which in practice it is useless. Usually in this case, a neighbor, if it is really far away, usually it is not the point we are looking for. And this query point probably just has it is outlier, and probably it just has no actual neighbor around it. So we are looking to add this distance-bounded k-nearest neighbor join in the next release, 171. Please stay tuned and looking forward to it. Okay, another question. So does repartitioning a Spark data frame affects partitions used in a KNN join? Yes. So at Euro, in regular spatial join or any kind of spatial join Sedona, so the performance of the spatial join is affected by the number of partitions in the data frame, right? It affects the query parallelism. So if you have more partitions, it usually will do better. Okay. Okay. Another question. So yes, the distance bounded k-nearest neighbor join. In that case, the distance is going to work like a threshold. So if there's no nearest neighbor within this distance, it will stop. Okay. Cool. Uh, let's move on. Okay, so yeah, I'm going to quickly go through the how to use the data frame-based readers. So the first one is the shapefile reader. Now it works with data frame directly. It preserves data types. You can directly use the Sedona.read.format shapefile and pass to the shapefile. Then it will give you the data frame with the geometry data column. The second one is the GeoPackage reader. The GeoPackage reader works with data frame directly as well. So the only difference here is you put the GeoPackage in the data source, right? It will be able to read any GeoPackage data. Okay. Oh, okay. Now let's talk about GeoStats. And the contributor of this GeoStats package, Spatial Statistic Toolbox package is here. Uh, James is here. Okay, James, I'm gonna hand over to you and uh, really looking forward to what you're gonna talk about.
Cool. Thanks, Jeff. Can you guys hear me? Awesome. And you can see me? I guess that part's not actually that important. And then hopefully you can also see my screen, which is a slide deck that says GeoStats in Sedona. All right. So yeah, I'm James. I contributed the GeoStats, let's call it module in Sedona. So who am I? I work at Whereabouts under Gia, senior geospatial software engineer. I was formerly doing maps learning in Amazon's last mile. We were doing things like trying to, update and improve speed limits in an automated manner based on, spatial data that was coming in from other Amazon teams and third parties. And I started using Sedona in its 1.0 release when it joined the Apache Foundation during that work at Amazon. So the goal of the GeoStats package was to implement spatial statistical algorithms in a scalable and parallelizable manner. So the first round of algorithms that we took on was dbScan, local outlier factor, and GeoSword's GI and GI star. So DB-scan is a clustering algorithm. This is something that in my experience, like DB-scan was far and away the number one priority in my mind. Um, I've personally had a lot of data scientists request to use it in my work at Amazon. I've heard it from customers at Wherebots, where I work now. Um, this is this has got to be the most popular like spatial algorithm, at least among, let's say, software engineers or programmers with spatial problems. Maybe if you were speaking to someone who was more of a geographer with a coding problem, they'd have a different answer for you. Um, and then here on the right side of the screen, I have like a sample of the code, the Scala code that implements DB scan. This isn't all the code, but I just wanted to show that there's nothing particularly like insane going on here to make DB scan work. It's basically just data frame code, the same kind of like data frame application code that you would write um, in Scala or Python if you were to, build an application on top of Spark, Sedona, and in the case of DB-scan, graph frames, which is a library that sits on top of Spark for performing graph operations. In DB-scan, it's a connected components. The second algorithm I implemented was the local outlier factor. So this it takes for each record in the table, you're trying to detect to what degree is it an outlier or an inlier. And basically what you're doing is taking a weighted average of the record's neighbors and how close it is to its neighbors compared to how close those neighbors are to their neighbors. This one, so the parameter here is K. LOF is very heavily reliant on having a performant K nearest neighbor join. So Feng's work to give us that KNN join was foundational here. Without that, I wouldn't have tried to implement local outlier factor. Um, and then finally, there is Geddes-Ord's GI and GI star. So these algorithms are for finding local hotspots. So the example I really like for this, I live in the Seattle area. There's, of course, Seattle downtown is a very dense area. But there's, of course, suburbs that have their own like downtowns or areas that are relatively dense compared to the rest of the suburb. So I should have included this photo on the slide. Didn't think to Jill just now, but I took all the Overture Maps Foundation data for places. It's like parks and businesses, like places with names, basically. And I'll come back to this question in a second. And I clustered them by their H3 cell, and then I ran Geddes-Ord's GI or GI star on those H3 cells and how many records there were in each. Um, and you can see the output basically gives you a heat map of these downtown areas, despite the fact that downtown Seattle is several times denser than the small town I live in, Issaquah. The downtown of Issaquah still resolves because it's a local hotspot. It's not like a global hotspot. So the results of New York City wouldn't like blow out the analysis, let's say, of a smaller city like Kansas City or something. The question here I'll answer, is there a stable and scalable implementation of dbScan in Apache Sedona? If so, are there any available benchmarks? Um, I haven't performed any benchmarks on the Sedona DB scan. Um, at the company I work at, we have like a similar product to Sedona, and I run similar code that this DB scan uses, but it's sitting on top of a different database engine. So the benchmarks I have from the internal product aren't fully representative, but with the different engine running this DB scan code, I was able to process. I've processed a few different data sets. I think I processed 100 million buildings in Europe. And I believe I processed the New York City taxi data set. Um, I don't remember the performance off the top of my head. Also, of course, without providing you the epsilon and minimum points hyperparameters I use, those numbers wouldn't be super representative because, the value of epsilon affects the number of core points you wind up with, which affects the number of points you're trying to perform the connected components calculation on. And that's really the crux here. In a world with Sedona and their performant distance joins, that part's pretty trivial, even up to like billions of records. So then this connected component becomes the bottleneck on the calculation of the DB scan. I'd be happy if someone else wanted to perform and publish benchmarks of DB scan, try to break it, try to crash it, compare it to whatever your favorite Java or Python or whatever implementation of DB scan is. Are there any plans to implement DB scan variants such as HDB scan? Uh, we'll talk about this in a slide or two. So yeah, that's what I have so far. And then I have some future work that is either in progress or like seems like a good idea, but haven't gotten to yet or haven't prioritized yet. So first I'd like to start with a call to action. Um, if you can write Spark code and Sedona code, you can contribute to the stats package. Um, so I'd love some help here, like bringing more algorithms into this. Um, Currently what I'm working on is bringing these into the SQL. Kristen, who's one of the biggest contributors to Sedona, he assisted me in building a system that replaces function calls with physical nodes. And so what we're going to do is call the data frame function that is already in Sedona on the RDD that you get inside the physical node. Um, and I've made good progress on that. That works. So that'll come out in, I don't know, 171 would be my guess. Um, I would call and ask for performance improvements. If you have changes to the existing code that you think could make it more performant, perhaps you're handy with GraphX and you think you can optimize GraphX to perform better than GraphAIMS does, or, I did an extra join that isn't strictly necessary or whatever. Please make those contributions to Sedona. Everyone will benefit from those improvements. Um, the other thing that we could do is add more functions. So, we could list a dozen clustering algorithms. I just picked k-means kind of randomly. Uh, Geometrically weighted regression is like a regression approach for multidimensional space. And as we see our anonymous attendee in the Q&A, there's a lot of enthusiasm for kriging. I've heard maybe 3 or 4 different requests for kriging. So if you want to contribute any of those or any other, spatial statistical algorithm that you can think of, we're happy to have the contribution. There's also an opportunity to add tools. So, hyperparameter selection for local outlier factor. There's some research around automatic hyperparameter selection for LOF. They use oh, what? There's like epsilon and min points, hyperparameter selection for DB scan. Silhouetting is a tool that one of my coworkers pointed out to me. I don't know much about this, but it's an approach for evaluating the quality of the clusters you generate from whatever clustering algorithm you choose to use. So if you want to help build tools that help us evaluate the outcomes that we get from using these statistical algorithms, that would be greatly helpful for practitioners who are leveraging these features. And then there's also variations on the existing algorithms. So someone had asked about hierarchical DB scan. There's also generalized DB scan, which is changing the height, like the criteria to draw an edge in the graph from strictly distance based to whatever you want. I will say there's a caveat with GDB scan, which is not all expressions give you performant joins. So if you have GDB scan may not always perform super well if it causes the query plan to fall back to a nested loop join. Um, and similarly, hyper or hierarchical DB scan, I haven't given any thought as to whether or not that can be effectively and efficiently distributed. I don't know. If you're motivated, I would be happy to see your work. The final one is DB scan with window functions. So this is how DB scan works in BigQuery and PostGIS. I can't remember if it's vanilla Postgres or if it's PostGIS. But being able to run the DB scan only over a specific window partition is how I see this implemented in other databases. And so having that functionality, I'm sure is valuable to some folks. DB scan, the connected components calculation can get very expensive when you run it on hundreds of millions of points. So where correctness is less important and performance is more important, being able to partition over a window is probably helpful for some people, or being able to partition over a window because your data set is comprised of different data that you don't want to cluster together. So with that, I'll just leave you with some contact information. My LinkedIn is James-Willis. My GitHub is the same. You can email me at work with james@wherebots.com. And I'm also on the Sedona Discord. I try to keep abreast of what's going on there. So if you have questions, comments, ideas, you want to chat, that might be the best place to reach out. Thanks all.
All right. Thank you, James. That's very exciting presentation. And now let's continue. Okay. So as James mentioned in his presentation, so we're always looking for help. So if you think you can improve the performance or even just contributing some notable examples, documentation updates, please feel free to participate. All right. Thank you all for your attention. And if you have any questions, please speak up and you can paste it in the chat. And now I'm gonna put you guys to promote you guys to panelists so you guys can talk. All right, so I believe I have invited all of you to become a panelist to the meeting. So if you guys has any questions, please feel free to open your mic and speak.
Hello, could you hear me?
Yes.
Yeah, I was wondering if you can refer us to a kind of a gentle introduction for start coding and submitting PRs to Sedona, how where we can start, or maybe if there are already tutorials or maybe some videos that will be kind of helpful for people that has me that we want to start to play with maybe some code, some Hello World, maybe that kind of stuff.
Cool. Yeah, that's a good point. So I can share with you some YouTube video. So we have
Okay, thank you.
yeah, James pays a good link. And as usual, so we suggest that you start with our Docker image. That is easiest to start because Docker image it actually comes with a bunch of example notebooks. You can play around with it and use those notebooks. And if you want to perform much more scalable query operations, you might need to look into some hosted service for Spark. Yeah, like I mentioned, so variables, Databricks, EMR, so on and so forth.
Oh well, but more than how to use Apache, yeah, I think it's more how we can contribute into the code.
Mhm.
Oh yeah, yeah,
Oh,
I can see pick announce attacks in Jira, develop a code contribute. Okay, yeah, yeah, I think that is perfect. Yeah, thank you. I think that is answer my question. The link in the chat answer my question.
Well, yeah,
cool.
the docs are pretty good on this question, assuming you use IntelliJ.
Oh yeah, that's a good point. Yeah, so okay, yeah, I'm a more Emacs boy, but I think Jira will works. I see. IntelliJ will work. Okay, thank you.
I have a question about the starter image, like the starter Docker image. So like when you start that up, it works great, which is awesome. But what like I don't know that much about Spark. I'm not very good at it. But when you do that, you get one node? Like, is there any parallelization happening when you do that, or is it just single node, like single thread doing everything when you do that?
So it is single node, but it actually leverage all CPU cores on that machine. Yeah. So of course, so there is some like there. I believe if you use the example notebook, so the notebook actually explicitly use all the CPU cores. Not explicitly use it always use all the CPU cores in that single node. There is some other setting that can actually only use one CPU core on that node. But the example notebooks in the Docker image actually leverage all the cores.
Um, I don't have a benchmark for this. It's just like a feeling I had from the work I was doing at Amazon. But when I would port like GeoPandas loads over to Sedona, doing joins on a single host, and that was like only in local development. And Prod always had a cluster, but I felt like it was going faster in Sedona on the single host than it was on GeoPandas.
All right. Any other question, folks?
No, I was just going to say I've tried DB scan on pretty non-trivial sizes now, and it's pretty amazingly fast, and doesn't suffer from big queries fast, but it has a something like 2 GB limit. You hit limits really quickly in BigQuery because of the way it partitions things. You're nodding your head, James. Yeah, so it's almost irrelevant asking about a performance comparison because beyond non-trivial data sizes, BigQuery just falls over. So
Yeah,
right?
that's kind of
You're
why
not comparing. Yeah. So
you can do things you
yeah,
just didn't do. Yeah.
yeah. So and thanks for fixing the zero distance thing.
Oh yeah, of course. It's released now, I believe. I think Gia pulled that into 1.7.0. In Sedona. In the whereabouts, I don't think I've cherry picked it, but I'll get to that today or something.
Shit, please do. I'm about to use that again.
Cool.
All right, folks. If you don't have any other questions, so we can end the office hour now. And as always, so the office hour is actually recorded, and we have a YouTube channel that actually posts all the stuff here. So actually, let me find it where it is. Uh, Yeah, paste it in the chat. So apparently it missed a few office hours, but we usually try to keep it up to date. So this one is actually being recorded. We will upload the office hour recording to the channel there. All right. Thank you all for joining us today, and looking forward to see you next year in January. Happy New Year, folks.
Thank
Bye,
you very
guys.
much. Thank you.